Hello, everyone. Welcome to our Monday. What is this? May 22nd stream. My name is Matthew. I'm one of the instructors for the course. So many of you are from the course, but if you haven't found us through our courses, then welcome from however else you found us. We're going to do a live session today. We'll go over how we structure this, and then I will hand it over to Chris, and we will take your questions live. So please post your questions in the chat. I will grab them from the chat. Actually, Vicky's grabbing them from the chat, and then we will kind of go in order as much as we can, but we tend to jump around also based on topic and just to give everybody a chance to ask questions. And so post those in the chat and we'll grab them from there. Chris, why don't you welcome everybody and we will get started.
Okay, yes, good to have everyone on board for a live session for our online classes or however you found us, and floor is open for any question on astronomy.
The very first question is from an email. Pramod Argade asks, is there any evidence pointing to a change in the distance between the sun and the Earth since the formation of Earth? So, they mention in particular after the collision with Theia that formed the moon, but also it could be due to migration or anything like that.
Right, so there are dynamical reasons to expect very small secular changes in the Earth-Sun distance. Generally, they would be to increase the Earth-Sun distance based on interactions with other bodies. But this measuring that is extremely difficult. It's now well known, and the reasons are well known, that the distance to the moon is increasing very slightly every year. I think it's 4 centimeters a year. But we don't measure the Earth-Sun distance with enough precision to see these very small changes. So they probably do exist from various interactions with external bodies, and also just by a very slow transfer of angular momentum and conservation of energy principle. But they've not been accurately measured.
Excellent. Thank you very much. The next question is from a live participant, Shani89, who would like to know how mirrors in telescopes work, and if you could talk a little bit why mirrors on Earth can detect the light from objects that are so far away.
So mirrors in telescopes are typically parabolic in shape, and that's because a parabola is the figure in 2 dimensions that will focus light to a point when it comes as parallel light from space. So we have parabolic mirrors, and in typical large optical telescope for research purposes, typically has a secondary mirror. So rather than just a single primary mirror focusing light to a point above it, you have a secondary mirror, and you essentially fold the optical path, bounce the light back down through a hole in the primary, and then focus it underneath the primary. The mechanical reason for that is because it balances the telescope better. If you had a very heavy instrument, and modern astronomical instruments weigh tons, hanging above the mirror, it's hazardous to the mirror, of course, and it makes the telescope very top heavy. Whereas if you fold the optical path and put the instrument under the primary mirror, it's a safe place to put the instrument. It's easily accessible from the floor of the dome, and it balances the telescope nicely. So that's a pretty standard optical path. The reason such mirrors can capture light from such distant objects is because of their size. Large optical telescopes now are 8 to 10 meters in diameter, and the numbers are going to go up to 20 to 30 meters in the next 5 or 6 years. And that's a huge amount of light gathering power compared to the eye, which is, just the pupil of the eye is a few millimeters, basically less than a centimeter, or Galileo's optical telescope was a centimeter or so. So you can now see objects that are billions of times fainter than the eye.
The next question is from Lawrence, who's on with us live. Hi, Professor. Is the energy density of dark energy constant and uniform throughout space? If so, as space expands, where does the new dark energy come from?
It's a good question. The dark energy density, if you like, or the force of dark energy causing the accelerating expansion of the universe, does seem to be independent of direction in the sky. So it's isotropic, is the physical way of describing that. And as far as we can tell, it does not seem to vary with distance from the Earth. And that it does indeed mean that as space expands, there's more and more dark energy available. The best guess as to where this comes from is from the vacuum itself, that the dark energy is a property of the vacuum. And so as the vacuum expands and more space-time is created, then more dark energy is available to accelerate the expansion. So it feeds on itself. The physical mechanism is simply not understood. We don't have a good physical theory for what dark energy is.
The next question is from Lee Smith, who asks, hi, what do you make of the recent behavior of Beetlejuice and the changes of brightness? Are there any good explanations or viable theories as to why it's happening?
So Betelgeuse is a supergiant star late in so it's a very massive star, and it's fairly late in its life. And, you know, when any star that is massive and evolved, it has multiple types of nuclear fusion going on in layers, sort of an onion skin structure. And that means it's intrinsically more variable or less stable than a star like the sun, which is just converting hydrogen to helium in one simple process. And any instabilities or changes in the fusion rate will ripple through the star and create other changes elsewhere. And so it's not unusual for any massive evolved star to have instabilities that will change its brightness. We can't diagnose the exact cause of the changes in brightness in Betelgeuse because we can't see the interior of the star. Remember, astronomers can really only directly see the surface of the star with an optical telescope. Interior to the star, it's opaque. And so it's really still a matter for some speculation as to what is causing the changes in Betelgeuse.
The next question is from an email from Hamid, who asks, you always talk about biomarkers when I think we should be looking for signs of artificial intelligence that are smarter, faster, and capable of interplanetary travel. So what kinds of, not biomarkers, but what kinds of markers could we look for to find these artificially intelligent machines, or to locate artificial intelligences?
So it's a good point that that biomarkers are just essentially designed to look for microbial life by its altering of a planet's atmosphere globally. If there's more advanced intelligent life forms, obviously they will have technology, and they could indeed have artificial intelligence and robots capable of traveling through space and exploring. So there is a branch of SETI, the Search for Extraterrestrial Intelligence, that looks for sentinels or alien probes. But you have to remember, it's an extremely difficult thing to do because space probes, ours are an example, are exceptionally small compared to the space they travel through. And so detecting that, it's actually worse than a needle in a haystack. It's like looking for a needle in an ocean. And so the strategies for looking for sentient probes or AIs in space is not even very clear how you would do it. Now, if they happen to be in the solar system observing us, then we can look for sentinels or alien probes in the solar system. But even within the solar system, it's extremely difficult to find a small object. And remember, we've used miniaturization of technology to make our probes smaller and smaller. CubeSats, you now have satellites that can fit in the palm of your hand. So I think that's the problem. It's not that we don't think such things might exist. It's the fact that there's no simple astronomical strategies to look for them.
The next question is from a live participant, Shani89, again, who asks, how can we really calculate the age of stellar objects?
It's not easy to calculate the age of a stellar object. It's not a direct observation. So basically, we only have any measure of age of a stellar object of any kind from inference from a model. So to do that, we actually need to take the things we can observe, which are the luminosity and the temperature. Those are directly observable, and then infer its evolutionary state that way. And so we don't really measure age directly. It's definitely based on a model. If you also measure the chemical composition and you know what fusion process the star is using, you can sort of work out how far through its lifetime it is in that sense of converting fusion products. But these are not accurate numbers. And so our measurement of stellar age is very rough, maybe only 10% accuracy at best.
The next question is from Wendy, who sent an email asking, I read that Saturn's rings will disappear in a few million years, and that Phobos, a moon of Mars, will break apart in some million years and make a ring around Mars. Can you shed any light on why these two things might happen? Why Phobos in particular, or just why the rings will disappear, why rings form?
I think the disappearance of Saturn's rings is projected, but not in a timescale of a few million years. Remember, that would be a tiny fraction of the age of the solar system, which would lead to a big coincidence and a problem in why the rings either took so long to form and then are disappearing, or why, having formed with this planet 4.5 billion years ago, they're now suddenly disappearing now. So I don't think that's going to happen. If there is a very slow dissipative process that occurs, and that's just natural attrition, or because you're dealing with rings of particles where there are collisions, and the occasional collisions will tend to scatter particles both in and out. And so there is a natural process just due to particle collisions within rings that will dissipate them. But it's a very slow and inefficient process. And so I think they're pretty durable, those rings. Phobos and Deimos, the small moons of Mars, are sturdy little moons, and the only way they would be disrupted is if they degraded in their orbits enough. Now, there is a very slight drag that operates on the moons of Mars because there's an extremely tenuous atmosphere of Mars that extends to their distance. And so that drag, that viscous force, will gradually cause them to degrade in their orbit and move closer to Mars. And at some point, the tidal force of Mars will disrupt the moons and they will break apart. But again, that's another very, very slow process. And we're talking tens or hundreds of millions of years for that to operate.
The next questions are from live participants. We have a couple people who have asked about careers in cosmology and astrophysics. Can you KP Athwaite asks, how does one find jobs as an astrophysicist in universities? And Harsh J asks, how did you become what you are today? So maybe you can talk about your journey professionally, and then how folks these days are finding jobs.
Sure. I mean, my path is still a pretty traditional path into astrophysics. My bachelor degree is in physics. It was at the University of London because I'm a Brit and I did a lot of my education there. But regardless of where you train, physics is the first degree of most professional astronomers and astrophysicists, because essentially you have to learn astrophysics. You're applying physics out into the universe. Now, some astrophysicists have as a first degree mathematics, some occasionally engineering subjects, and sometimes they actually do have an astronomy undergraduate degree, but those are still quite rare. So physics is the sort of basic training, if you like, for an astrophysicist. Then you go to graduate school and you're going to do a PhD at that point in astronomy or astrophysics. The two are really considered interchangeably. And in the graduate program, you'll be getting additional courses at the level of master's in astrophysics, physics basically, sometimes planetary science included there. And that's your training. And the PhD is the sort of base requirement to be a professional astronomer in a university setting. Now, you can be a professional astronomer without a PhD in other settings at some observatories, operating as on the technical side, on the computing side, and then perhaps even when you're a telescope operator, some of those people don't need advanced degrees at all. I think you do usually need a bachelor degree in science and probably astronomy. So there is more or less a standard path into a career in astrophysics.
The next question comes from live participant Goldilocks Zone. What do you think of the theory that comets or asteroids could have brought primitive life forms such as bacteria from another planet to the Earth?
So this idea is called panspermia, the idea that life travels through interstellar space, carried by small rocky bodies like comets or asteroids. There's no direct evidence to support it. Our best guess at the moment is that life started on the Earth entirely from initial conditions on the Earth in a chemical soup that gradually turned into a biological soup with natural selection and single cells. So far, all we can do is look at spectroscopy of comets and asteroids and other objects out in space and look for complex molecules. And certainly amino acids and some molecules with 20 or 30 atoms, so quite complex molecules, have been found in comets and asteroids, but nothing like a single cell or a chunk of DNA or RNA. So there's no direct evidence by observation that these small objects can harbor life. That's on their surfaces. Admittedly, that doesn't speak to their interiors. And so is it possible that life could be entombed within a comet or an asteroid, protected from cosmic rays? And yes, it is possible, because we can't rule it out directly. But at the moment, there's no evidence, compelling evidence, to suggest that that's how life moves around in space. Most people think that life starts from initial conditions on a particular body, like a planet.
They have some follow-up questions, which is, could something like this, could this panspermia idea have be applied to any other planets in our solar system? Which other planets could that have happened, and would that, if that happened, would that mean that other organisms we find would be genetically similar to us?
It's certainly possible for rocks to travel through the solar system. So interplanetary transport is extremely inefficient. Now, independent of whether life could exist in a rock that travels through interplanetary to interstellar space, it's very unlikely that a rock from one star system will land on a planet in another star system. Numbers are incredibly small. Within a planetary system, though, there is a transport mechanism. It's because objects are being bombarded by meteors, and then the impacts can throw off debris. That debris can travel in space. So we know this happens because we found 100 plus Martian meteorites. We've found some lunar meteorites. And people might speculate that there are Venusian meteorites, though no one's definitively claimed that. So we know rocks can travel from Mars to the Earth, and some rocks could go the other way. And it's indeed conceivable, because of impacts, that rocks could travel between any of the terrestrial planets. It's going to be more favorable when it moves in the direction of the sun, because the sun's gravity operates that way. And it's more favorable when the planet being impacted is lower gravity and a thin atmosphere. So the transport from Mars to the Earth is much more efficient than the transport from the Earth to Mars. And that does indeed leave the door open that life got to Earth from Mars. We think life may have existed on Mars 3 or 4 billion years ago, and that raises the possibility that life on Earth formed initially on Mars and was seeded there. And really, the only way we can disprove that is by finding ancient microbes on Mars that have a totally different genetic basis than microbes on the Earth. That's some way off in the future to show that.
Krutika 1114 is an engineer in India and does research on battery technology. What do you think is the future of lithium batteries in regards to space exploration, or generally, what do you think that the power requirements for future space missions? How will we deal with that?
So powering space missions is quite a big issue, because you need compact energy sources. It's also true, though, lithium batteries are very favorable, because again, it's a low atomic number element. If you're talking about lead batteries, the sort of old-fashioned kind, then that's one of the heaviest elements. So that's expensive to get that to launch a battery that includes any lead. Really, the best prospects for powering space missions are using solar energy and storing the energy locally on the spacecraft. So using the sun's energy, because that's available all the time, and then using radioactive decay. So fission reactors, plutonium small reactors, have been used in planetary missions for 40 or 50 years, and they will continue to be used because when you travel far from the sun's radiation, of course, declines with the inverse square law, and so solar power becomes far less efficient. So I think it's going to be a while before any battery technology to maybe store solar radiation will eclipse what we can do with radioactive decay and nuclear power.
The next question is from an email. Richard Caruth asks, in regards to the Big Bang, what do we know, believe, or hypothesize about the source and initial start of it? What things had to exist or happen for it to occur?
So the short answer is we don't know. The Big Bang Theory does not posit a cause for the Big Bang, and it doesn't speculate as to what the actual initial conditions were. We just know that we're talking about conditions of exceptionally high temperature and density. And we get to the point extrapolating backwards to the tiny fraction of a second after the Big Bang, where the laws of physics are simply inadequate to describe it. So disappointingly, perhaps, the Big Bang Theory says nothing about what caused it, says nothing about what came before. And it's a realm of speculation, which cosmologists are happy to indulge in. And I've answered previous questions about that, but it's fair to point that it's not conventional, affirmed science yet.
Excellent. So that's Harsh J should answer the question you asked, that we don't know what caused the Big Bang. The follow-up question is, was all matter created out of nothing, or did matter come from somewhere else?
The Big Bang, as far as we can push the theory, does talk about quantum genesis, speculates a time 14 billion years ago, roughly, where the universe was smaller than an atom, so it was on the scale of a quantum entity. And it is indeed part of the inflationary scenario that the energy, the impulsive energy for the expansion of the universe came from the vacuum. So indeed, it was borrowed from the vacuum, if you like, of space. So that's the best we've come to in terms of saying what a cause of the Big Bang is.
Excellent. The next question is from Astrocellist, who asks, if you happen to see the supernova in M101, or the Pinwheel Galaxy, that was observed over the weekend, do you have any interesting observations or anything that you could share about supernova in general?
So we observe the nearby galaxies. M101 is a very nearby bright galaxy, obviously part of the Messier catalog. So these are the biggest, brightest, and closest galaxies we know of. And they're all being monitored for supernovae. So finding a supernova in a nearby galaxy like that is very exciting. We get a lot of information. And in general, supernovae tell us a lot about dying stars. They tell us how heavy elements are created in the universe. They confirm, or maybe potentially deny, our theories of the late stages of stellar evolution. And supernovae are valuable as distance indicators, type 1 supernovae in particular, which are the supernovae that form in binary systems. So every supernova is valuable because it allows you to do research on distance indicators in the universe. And I think the physics of supernova is also better understood than it was 20 years ago because of supercomputer simulations. So this is a fairly mature field of astrophysics now. But we still learn from every nearby supernova that we measure. And we're waiting, of course, for one in the Milky Way.
The next question is from an email. Wendy asks, I know the Oort cloud is hypothetical, but is it possible that the Milky Way galaxy itself has something like an Oort cloud surrounding it, given that the universe contains many examples of symmetry in various types? So this would be like a symmetry of scale.
So the Oort cloud is hypothetical, but it's pretty good inference that the Oort cloud exists. We know that comets come into the inner solar system, and we can see from their orbits that, and by Kepler's law, that these comets, which are occasional and short-term visitors to the inner solar system, must spend the vast bulk of their time in the outer solar system. So just from the comets we know, we can infer a population of distant comets that are far from the Earth in their orbits, that are dark because they're not illuminated by anything. Now, calculating the full census of comets, which ends up being about 1 trillion in round numbers, an incredible number, there's a lot of speculation that leads to that number. As for the Milky Way doesn't have a directly analogous situation. However, the Milky Way, the visible stars we see in the disk of our galaxy and in the halo, do seem to be embedded in a large dark mass, which we think is dark matter. So that's what the quasi-spherical encompassing space around the Milky Way contains. It contains dark matter particles, the nature of whom we do not yet understand.
The next question is from Shani89, who asks, how can we teach the general public about some common misconceptions in astronomy?
Well, everyone who teaches astronomy does that. That's what we do in the classroom all the time, especially with non-science majors. So you try and address the misconceptions that you know and that people read about. More generally, it just means, going out in public and giving talks. Amateur astronomers are often very good at this because they know the sky, they know quite a lot of astronomy, and they go out to their clubs and to their local communities and give astronomy talks. So people just have to get out there to telling the story of astronomy through the conventional and affirmed facts of astronomy. And every time you hear a question or see something online as well that is a conspiracy theory or just blatantly false, then just as gently as possible and firmly as possible, you should rebut it. And the more people that do that, the better off the science will be.
The next question is kind of a follow-up from an earlier discussion about the Big Bang. Harsh J, and I'm not sure the premise is correct, but you can address that. Harsh J asks, why do we believe in the theory of recreating universes? And I assume that means universes collapsing and then expanding and things like that.
So the idea of recreating or continual creation and destruction of universes is embedded in the theory of eternal inflation. So eternal inflation is a variation of the inflationary scenario, which extends it in the time axis essentially to infinite time in the past and infinite time in the future, where in parallel and independent of our space-time and our expanding universe, there are other space-times that are expanding and collapsing and so on, and sort of endless cycles of creation and recreation. There is no direct evidence for eternal inflation. That's the most important thing to say. It's a speculative variation on the basic inflation idea, for which there is some evidence. So I would say that the creation-recreation idea is something that's in the realm of speculation.
The next question is from Lawrence Carr, who asks, after the Big Bang, how did real matter and dark matter form and overcome the anti-gravity of dark energy?
So in the early universe, if all the components of the universe were in place at once, the early universe was very small and it was very dense. So the normal matter and the dark matter were all very close together. All those particles were very close together. So the density of normal matter and then dark matter being even stronger overwhelmed the force of dark energy. Dark energy has really only come to dominate the universe and its expansion in the last 4 or 5 billion years. So for most of the first 2/3 of the history of the universe, matter and radiation were the things that dominated. In the very early universe, before 10,000 years after the Big Bang, the universe was radiation dominated. So the photons and the energy associated with the photons was causing a radiation pressure, an outward pressure, and that was the dominant force. Gravity, meanwhile, from the dark matter and the normal matter was retarding the expansion or causing a deceleration. And so for the first part of the universe's history, we do see decelerating expansion. And only when the dark matter and the normal matter have diffused out to become very dilute does dark energy take over, and we have accelerating expansion as we see now.
The next question is from Ron CC1, who says, hello from Paris. How can we explain the important tilt of Uranus? Does it come from a collision with a massive object, or is there another explanation?
It's most likely a collision with a massive object. We also have a counter-rotating planet in the inner solar system, Venus, which spins in the opposite direction relative to the other terrestrial planets. And in other words, its angular momentum vector is 180 degrees from the angular momentum vector of the inner planets and the sun itself. That's pretty strong evidence that Venus suffered a collision. And so we infer the same mechanism for why Uranus is tilted on its side and so has extremely long seasons given its long orbit. But tracing the nature of that collision is impossible to do after so long. It's probably happened billions of years ago. So whatever the interloper was, just long gone. Also, Uranus is in the outer solar system and so is more vulnerable to influences from external objects. So it's possible that rather than an actual collision, it could have been a couple of very close interactions or encounters gravitationally without a collision. You can dynamically simulate these, and you can show conditions under which Uranus's tilt could have shifted, but we don't really have any way to decide between these scenarios.
The next question is from Wendy via email. I read that the moon is moving away from Earth and wonder why the Earth's superior gravity isn't maintaining this separation distance.
So it's a standard gravitational effect, actually. The Earth-Moon orbit, where the moon is by far the less massive object, but is also relatively close to the Earth. Now we have a tidal interaction, which causes the moon to tidally lock to the Earth and always point its same surface. So what we actually have is a very slow transfer of energy and angular momentum, where the moon is gradually moving further away from the Earth, and the Earth is gradually spinning down. So you're essentially, to create this extra angular momentum of the moon, you're taking away a little bit of the Earth's angular momentum and slowing the spin rate down. And so the day is getting very, very slightly longer as the moon gets very, very, very slightly further away. So this is a standard gravitational interaction, and it reflects conservation of angular momentum and energy.
Wes in all caps, who's on with us live, asks, what advice or resources would you give to someone who has a genuine interest in astronomy, but doesn't know what resources to use to continue learning?
Well, there are many books, of course, on astronomy. I've written a number myself, and there are some really good online classes. And if you're on this session, you probably know about our astronomy class and our astrobiology class and our history and philosophy of astronomy class. And these MOOCs are free, and there are others as well by other instructors and people around the world, actually. So I would say online courses, especially the MOOCs, which are free, are your best way to learn, because you can learn asynchronously. You don't have to sit in a classroom or go to a particular place. You can do it online. You can watch the video lectures as you have time. You could download them sometimes on your computer and watch them when you're on the road. And you can choose to do the quizzes and the other evaluations or not. It's not required. So that is, I think, still the best way to learn. And the other way to learn, of course, is to look at the media that cover astronomy routinely. In the major journals, it's a sort of unusual thing. You will get occasional astronomy stories in the New York Times and the Washington Post, those major online newspapers, or periodicals. But generally, there are Science News will have astronomy stories more or less every week. Science Magazine will have astronomy stories every week. The Science Daily is an online, you can get the RSS feed on astronomy and space, and you'll get multiple stories a week. So there are plenty of ways to keep up with what's going on in the field.
The next question is from Akim, who sent an email. Can you please shed some light on recent comments that they've read in cosmology concerning or that the Big Bang theory may no longer be valid based on latest observations from the James Webb Space Telescope?
Yeah, I have to say there's some very sloppy reporting on these topics, where the Big Bang is dead is sort of a headline, not quite in those words, that you might read every few months or certainly once a year. I think the allusion in the most recent reports for James Webb relates to the fact that we found some very big, well-formed galaxies very early in the history of the universe, and that's considered a challenge to the Big Bang. The truth is, it's not an actual challenge to the Big Bang model, the idea that the universe started in a hot, dense state. What it is a challenge to our understanding of how galaxies form and grow, and that's a more complicated thing, because it involves gravity, involves hydrodynamics, involves star formation, it involves, things that are quite complicated. So the simple truth is that the Big Bang model is not in any great jeopardy. It's still very sturdy and standing strong. But we are definitely learning things about the early universe from James Webb and other ground-based telescopes that suggest we don't know all the astrophysics of the early stages of star and galaxy formation and black hole formation too.
Pramod Argade would like to know, how are elements beyond iron formed in a fraction of a second during a supernova explosion?
So in the supernova explosion, when the core of the star collapses because it has no longer pressure support, because iron is the most stable element. So at that point that you formed iron, you no longer get enough energy from nuclear reactions to keep the star core intact. It will collapse. And in its collapse, it creates an enormously dense state of matter, because what's left behind a supernova is a neutron star or a black hole, and sometimes nothing. And then the shock wave going inwards bounces to a shock wave going outwards, and that meets the outer envelope of the star and heats it up to an enormous amount, in that blast wave. Essentially, the temperatures can reach several billion Kelvin in that blast wave, and that temperature is easily sufficient to instantaneously, in very short time, fractions of a second, cause the fusion of all the atoms, all the elements in the periodic table up to and including uranium and the transuranic elements, actually. So it's just a phenomenal energy deposition in a blast wave of a supernova that causes this heavy element creation.
The next question is from Kritika1114. In places where there's really no access to solar energy, and we have to use nuclear power, do you have any concerns about the waste or nuclear material and its use in these projects?
It has been a concern. Congress actually has weighed in the United States because NASA has been using plutonium reactors in its spacecraft since the 1970s. And the government got involved because people were worried that, these spacecraft, when they were in Earth orbit or near Earth orbit, or even came back to the Earth to have a gravitational assist after launch, might crash into the Earth and cause radioactive contamination somewhere. First of all, the amount of plutonium, amount of radioactive material in a small spacecraft is actually pretty modest compared to a big nuclear reactor. So it's not a very proportional concern. Also, the likelihood of that kind of a disaster is very low. It's never happened, for example, with all the dozens of space missions NASA has. But that's really the only reasonable way to get energy very far from the sun. So it's quite likely that nuclear reactors will continue to be used. There are safeguards because NASA is a government agency. It's subject to regulatory approval and regulatory oversight. So I would say the safeguards that are taken with the reactors on NASA spacecraft, before launch and after launch, are actually pretty stringent and carefully controlled.
Dave McKenzie sent an email. Do astronomers know what the Great Attractor is and how it is affecting the Milky Way galaxy?
So the Great Attractor is a designation that goes back, I think, to the 1980s, to the first large galaxy redshift surveys. The Great Attractor was as we know, galaxies cluster, and because of those clustering, galaxies have motions. So the Milky Way is moving towards Andromeda and vice versa, and both galaxies and the local group are falling into the Virgo cluster. The Virgo cluster is part of a large supercluster, and as people went on larger and larger scales, they realized that our entire galactic environment, including Virgo, was moving towards something that was designated as the Great Attractor. And it was presumed to have an enormous mass, 10 to the 15 solar masses. So that's tens of thousands of times the mass of a single galaxy. Evidence that a single coherent structure called the Great Attractor exists has actually got a lot weaker over time. As people done more galaxy redshift surveys, the sort of demarcation of a large thing and large massive aggregation of galaxies in one region of space is kind of weakened. This object is not a single object, perhaps. It's probably not gravitationally bound. That's almost certainly the case. And people have actually stopped using the term Great Attractor in the last decade or so.
The next question is actually back to the previous question a little bit. I misunderstood. It was a great answer. But what they were interested in also is, what are your thoughts on the possibility of using nuclear waste as power for space missions? Do you think that would be an answer to the problem of nuclear waste here on the Earth?
I think nuclear waste is not an efficient enough power source. So this is radioactive material that results from nuclear reactions in power plants. And it's not high enough densities, not high enough specific energy. Specific energy is how much energy you get out per unit mass. Nuclear weight has low specific energy output. And so it's not really efficient enough for spacecraft purposes. However, I would invert this issue and say that the reduction in the cost of launching material into Earth orbit, thanks to SpaceX and Blue Origin, is going to give us a solution to our nuclear waste problem on Earth, because obviously we don't want to put it deep in the ocean. Underground is not even safe necessarily. And so what do we do with this waste? Well, sending it into space, in deep space, or into the sun very slowly, is an ultimate solution. And the cost per kilo of launching to Earth orbit is now coming down to the point where sending it into and beyond Earth orbit, so leaving the Earth forever, is as cost effective as the things we do with it when we look at deep ocean internment into, in canisters in the deep ocean trenches or deep within a mountain. So I think we're within sight of a space solution to our nuclear waste problem.
Stephen Tampa would like to know if you're familiar with Professor Kaler's works and his some of the somewhat dated books that he's written. I'm assuming they mean Jim Kaler from University of Illinois. Are you familiar with his work and with any of the books that he's written as popular literature?
Yeah, he's a colleague that I've met several times. He's pretty old. I know he's retired, and I think he's still alive, but he must be getting pretty old by now. And he's written good books. He wrote a couple of classic textbooks, actually, 20, 30 years ago. So I'm aware of his work, and he has high standing and high reputation in the field of astronomy. So he's a good educator, good popularizer, and his books, I think, are very high quality.
The next question is from an email. Do periodic comets lose mass with each transit to the inner solar system?
Periodic comets that come in very close to the sun, so sun grazing or inner solar system comets, they are definitely losing mass, because as they reach the interior part of the solar system, then the solar radiation is heating them up and boiling off the volatile materials. So comets are, mixtures of frozen ices and rock, and the rock is basically intact, but even some small amount of particles are lost. But what is really lost are the volatile materials, the frozen gases. And so each transit through the inner solar system, a periodic comet that comes close to the sun, will lose some mass, some material, and also will gradually be drying out as it loses its frozen liquids. And that's a process that continues throughout the life of a comet.
The next question is from Goldilocks Zone, who's on with us live. If Earth did not have an ozone layer, could life still exist here? And if so, how might it be different?
If the Earth didn't have an ozone layer, the level of cosmic ray, UV radiation, and damaging material, damaging radiation to genetic material would increase substantially by factors of several. That alone would not preclude life. It would cause much higher mutation rates and cancers and things like that. However, inside the oceans where a lot of life exists, or under the surface where a lot of life exists, we are pretty much immune from the extra radiation, because solar radiation, cosmic rays, ultraviolet, doesn't penetrate more than a few inches or up to a foot through the water. So all the deep oceans will be immune from what would happen if the ozone layer disappeared.
The next question is from Cosmegi, who asks, can you talk a little bit about what nuclear astronomy is, and how someone could get involved in that as like a career?
Not totally sure what that phrase refers to, so I'll just have to guess. Nuclear astronomy may involve astronomy of nuclear processes, so because they are part of astronomy, and that includes things that happen in the cores of stars, or anything, that involves fusion or fission in astrophysics, and there's a number of those processes. Nuclear astronomy also could involve what was the subject of recent questions in this session, the idea of using nuclear power to power spacecraft or space probes, and that will continue. So assuming that's what nuclear astronomy means, it's not a phrase I'm that familiar with as a phrase. So that's my venturing as to what it might mean.
Excellent, makes sense. Let's see. Akshata asks, in the molecular cloud, can only one solar system form, or could many solar systems form from one large interstellar molecular cloud?
Yeah, molecular clouds tend to be large. And so the general case is that many solar systems, many stars, and many planet systems will form from one molecular cloud. Perhaps the best example, because it's a very bright object that you can see with your naked eye, if you have a good eyesight and a dark sight, is the Orion Nebula. So within the Orion Nebula is the Orion molecular cloud. And that's been known for some years, since we had good infrared observations. And so going back 30 or 40 years, infrared astronomers detected a giant molecular cloud inside the Orion Nebula and have seen the formation of young stars. There's a cluster of stars called the trapezium, which is 4 embedded stars. And they're just the brightest examples of probably dozens of stars that are forming in this dense molecular cloud. There are other molecular clouds that have been studied in the Taurus Nebula that have the same thing going on. So basically dozens or hundreds of stars could form from one giant molecular cloud.
Excellent. The next question I kind of enjoy. Nobody Naxos asks, if we accept that 95% material and energy is dark in the universe, how can we really make theories about the universe and be confident that they are accurate in any sense?
It's a good question, and it is a big limitation on cosmology. So we infer the existence of these 2 dark components of the universe, dark energy and dark matter. The dark energy is 3 times stronger in its effect on the cosmic expansion than the dark matter, and they together form roughly 95% of the universe. And so we just have to accept the inference of their existence. The evidence that dark matter exists and is that big a component of the universe is multifaceted, based mostly on gravitational lensing, which is a very hard to get around that evidence, since mass bends light and dark matter will bend light just as well as visible matter. So it is pretty hard to refute the existence of dark matter given gravitational lensing. Dark energy's evidence really rests with the accelerating expansion of the universe. And again, no one's come up with an alternative explanation for why that's happening, and no one's shown those observations to be wrong. So we're in an awkward situation, to be honest, in cosmology, where we have a mature model, Big Bang, and a lot of evidence that that is the case, but we have 2 components of the universe that dominate it that we don't physically understand. And so that means there's some excitement ahead in cosmology.
The next question is from P51, who asks, what is the closest distance where the magnetic field of the Earth, they ask about reconnecting due to solar flares. I guess the question is really about, can you just talk about how the magnetic field of Earth is affected by solar flares, and how far away from the Earth something needs to be affected by a solar flare so it won't be protected by the Earth's magnetic field?
So the Earth's magnetic field is absolutely affected by solar flares, because solar flares involve high energy charged particles traveling from the sun to the Earth very rapidly, not at the speed of light, but at hypersonic speeds. And when those particles impinge on the magnetic field of the Earth, they tend to spiral along the field lines and to generate high energy radiation, because a charged particle in a magnetic field line will radiate. That's a synchrotron process. So we know there are these interactions, and occasionally, yes, the solar radiation is strong enough that it disrupts the Earth's magnetic field on small scales and causes magnetic field lines to break apart and then reconnect. So it can disrupt locally Earth's magnetic field, not globally though. So we see this effect during solar flares, and that we can measure it because as the solar flare energy hits the Earth's magnetic field, we see a lot of effects. The aurora, of course, is a spectacular version of these effects.
The next question is, I don't know whether this statement we talked about in a previous live session, or whether this is something from, that the viewer read. But they read this statement: there are reasons we might need to move on from general relativity. Do you agree with that as a statement? And can you expand on why that might or might not be the case?
It is true that general relativity is not the final theory of gravity. So that's a simple statement that is true. And the reason we know that is because general relativity does it very well, explaining gravitational phenomena, but general relativity cannot be reconciled with quantum theory, the other great theory of physics that we have. So we have these two great theories of physics, each successful in its own realm, each of 100 years old or so, that are incompatible. And so to have a theory of gravity that can also incorporate the effects of subatomic particles is really important, and because otherwise we can't understand things like Hawking radiation and black holes. And that theory is not with us. So that is a good argument that general relativity is not the final answer, that it's worth working on more sophisticated or more advanced gravitational theories. The problem is that it's a very difficult work. And the bar is set very high because any alternative or superior gravity theory you come up with has to do everything that general relativity can do and then more. And general relativity has been incredibly successful in many different regimes. So again, the bar is set very high. It doesn't mean people aren't doing it, but I would say there's no superior gravity theory within sight right now.
Rutika 1114 asks, it says a general question. What do you think? What do you think is the future of space exploration, let's say in the next 10 or 20 years?
Well, the private sector is reducing the cost to get to Earth orbit by large factors, an order of magnitude in the last decade. And that's meaning that we'll be able to put things into orbit much more easily and cheaply. That in turn means that we'll be able to assemble things in space and then move them around the solar system in ways that would be too expensive in the past, or things that would be too heavy to launch from the Earth's surface where the gravity is so strong. So I think on the timescale about a decade, space exploration will become much more exciting because we'll be able to have much bigger spaceships, including some containing people, but also interplanetary probes that we assemble using, 3D printing and robots in Earth orbit, and gives us an enormous number of extra options of how we move around the solar system and what kind of exploration we can do.
The next question is from Zshan612. So we've talked a little bit about how to get into astronomy as a career, typically on a PhD path. But they'd like to know if you can talk about some career opportunities after completing a bachelor's degree in astronomy astrophysics. What are some of the career opportunities at these early stages?
So after a bachelor's, you definitely have some employment opportunities. They include working for, say, one of the private space companies, many of which there are 3 dozen pretty much now based in the US alone. You could work for any of the major observatories. Not all those positions require an advanced degree. You could work for some government agencies. NASA, of course, hires a lot of astronomers. And again, they don't all have to have PhDs or masters. And there are some, there's some other space technology companies that do astrophysics type work in the private sector. So there are a fair number of opportunities. And if you have programming skills to go with your astrophysics or astronomy bachelor, then you're highly employable.
Excellent. The final question for today. So we just got a couple of minutes left, and I think this will round us out for today. One of our students would like to know if you could talk a little bit about the theory behind the collapsing universe and whether you think that is likely to happen, and if not, then what else?
So the idea that the universe might collapse in the future is not looking like a plausible outcome given what we know of the present situation of the universe. So unless dark energy has a very strange property that we've never measured, where it decays in strength, for example, dark energy has the properties we've measured so far, then the universe will continue in its accelerating expansion. And that makes the likelihood of a turnaround and a subsequent recollapse very low. Basically, some new physics principle would have to come into play, or something would have to change dramatically. So recollapsing universe is not a current option within conventional cosmology, but the big asterisk we always put beside that is the unknown nature of dark energy. So good questions as always, everything from space travel to cosmology. And thanks for being online with us. Thanks to Vicky and Matthew for facilitating. And I can't remember if we have the next one lined up. We usually work ahead, so we have the next one penciled in. I'm away for roughly 2 weeks in early to mid-June, so we'll try and work our sessions around that trip.
Excellent. We do not actually have our next our June sessions scheduled yet, but we will get those out to everyone as soon as we schedule them. And I forgot to mention it before, but stick around here on this channel. We're going to roll right into the next stream. So stick around, and Vicky has some fun stuff planned for you all. I believe they're going to be doing an amateur astronomy stream with Vicky and Aiden. So we are excited to have been here with you today, and we hope you stick around for that stream. And we will see you in a few weeks on our YouTube channel. Take care, everyone.
Bye. Bye.